Okay, chapter 6 is all about Laplace transforms. And it's gonna take a while before the pieces sort of come together and we have a sense of what we're doing and why we're doing it. Okay, it's gonna feel kind of weird. So I'm just gonna give you a big picture summary right now. Basically, what we're gonna do in chapter 6 is we're gonna work really hard in order to be lazy. Okay, so I think we can all agree that algebra is simpler than calculus in most cases. So if I have a differential equation, that tends to be a hard problem to work with, whereas if I need to solve an algebraic equation, that tends to be a lot simpler. Okay? And Laplace transforms are going to take differential equations and transform them into algebraic equations. So that's going to make them easier to solve, and we'll solve the algebraic equation, and then we'll go back and we'll have a solution to the differential equation. Oh my goodness, feels like magic. Okay, so here's some important terminology and notation. We're going to have f, that's a fancy looking f that I'm not very good at drawing, but that's going to be the set of functions of t defined on the interval from 0 to infinity. So defined for all non-negative numbers. Now, one important note here. I did not say that the domain is limited to this. So I didn't say that my functions aren't allowed to be defined on negative numbers. So things like our exponential functions and sine and cosine, which we've really come to know and love this semester, those are defined from 0 to infinity. They happen to be defined elsewhere. For the purposes of Laplace transforms, we don't really care, okay? But it's not that these are the only places that they're defined, it's that they must be defined for all non-negative numbers, okay? All right, we're going to have g, that's a fancy g, and this is going to be the set of functions of s. And if I'm using set notation, I really didn't need to write the word set. It's just the set of functions of t defined here. G is going to be functions of s. As we'll see, some of those functions might have some restrictions on their domain, others of them might not. These are just functions of a different variable, s. Okay. The Laplace transform, which we're going to write as this fancy L, that's going to be essentially a function that sends functions that are elements of f, so functions of t that are defined on non-negative numbers, to g, to functions of s. So it's going to take a function of t, that's the input, the output is a related function of s. Generally the notation is if I call my function of t y of t using a little y, I would say the Laplace transform of it is capital Y of s. So I use capital letters for the associated function that's a Laplace transform, and very important, it's a function of a different variable s. Similarly, if I were to write f of t, then when I took the Laplace transform, I would write capital F of s. Okay. And what the Laplace transform is going to do is if I apply it to both sides of an equation, it's going to take a differential equation in my function of t, which I could call y of t or f of t, and it's going to send it to an algebraic equation in the related function, capital Y or capital F, whatever notation I choose to use, of s. Okay. So, here's basically a picture of what we're going to be doing. So, here I have the land of f. So these are my functions of t that are defined from 0 to infinity. And here I have the land of g, that's my functions of s. I'm going to start over here with a differential equation in y of t. I'm going to apply my Laplace transform, and that's going to give me an algebraic equation in y of s, in the Laplace transform of this function. Okay, so basically step one, I'm going to apply the Laplace transform to both sides of a differential equation. The result will be an algebraic equation. So, we're good at algebra. We're going to solve that equation. So step two, we will solve. Okay? So, this is basically a differential equation where y of t would be an unknown function of t. So solving this equation would be finding that function. This is going to be an algebraic equation where capital Y of s is an unknown function of s. I'm going to solve that algebraic equation for s, and that will be my solution to that algebraic equation. I feel so clever for pointing that out. Okay, then I'm going to translate that back. Didn't mention this yet, but this is an important property of Laplace transforms. They are invertible. Now, in math, so many things that we do, we subsequently decide we want to be able to undo. So we have addition, we want to be able to undo it, we have subtraction. We have multiplication, we want to be able to undo it, we have division. Okay? So Laplace transforms are going to be invertible. This function, whose input is a function of t and whose output is a function of s, is 1-to-1. So it is invertible. So step 3, and I'm running out of space here, so I'm going to just move over and write step 3 over here, is apply the inverse Laplace transform to the solution you got for y of s. In other words, we found the function that was the solution to this algebraic equation, and that result is the answer to our differential equation. So that's going to be our solution to the differential equation. So like I said, we're basically going to work really hard to be lazy. We're going to start with a differential equation. We're going to say, oh, those are hard. So we're going to apply this Laplace transform, say, oh, all I have to do to solve this new equation is some algebra. I can do algebra. We're going to do that algebra, and then we're going to translate that answer back using the inverse Laplace transform to get our solution. Okay. So that's our game plan. We still need an awful lot of definitions of things. So in the next video, I'll give you the definition of how this L function, how this Laplace transform is defined, and we'll do an example of it.